ESET 365 final report, remote control car with the HCS12 microcontroller. Our goal is to design and build a wireless remote control car from the given parts in the course kit. To create a program that with the input commands would control the servo motors and therefore drive the car. To test the developed car on an arbitrary test course to prove the functionality of the car. Here you can see a list of the equipment used to develop the RC car and a list of the parts included on the RC car. Down to the basics. In this slide you can see a transmitter, a receiver connected to an HCS12 microcontroller, and the servo motors connected to the HCS12. The entire project can be broken down into separate projects, each consisting of design, development, and testing. In this case, being a transmitter, a receiver, a servo to HCS12 interfacing all units, and program development. All parts together create an integrated system that we will call an RC car. In this case, 4 buttons are to be pressed on the transmitter side. The receiver circuitry would read those buttons push, and those buttons signals would then be directed to the input of the HCS12 microcontroller. The microcontroller, which controls the servos, will then move them based on the user inputs and buttons pressed. The transmitter. The transmitter is composed of a serial encoder HT6014 based on the address pins A0 to A7 and the data D10 to D13. The encoder sends serial trails of pulses to indicate both its ID source and inputs. The speed of these trails is determined by the OSC1 and the OSC2 resistor. The serial trail is fed into the input of the 434 MHz TLP424A radio transmitter and eventually broadcasted out. A small search around the house led me to an older wireless computer remote control which had 4 normally open buttons I could use to control the inputs of the HT6014. I took the internal electronics PCB and replaced it with my own breadboard, which I managed to fit. I then fitted a 9-volt battery on the back, and there was no need to use a voltage regulator since both the HT6014 and the TLP424A are rated for 2 to 12 volts. Confirmation on my oscilloscope showed me a trail of TTL data each time I pressed any button, which was different for each input combination. With 2 buttons per servo, this would allow for forward, reverse, left and right turns, and even left and right spins. The receiver. The receiver, like the transmitter, really consists of 2 parts, a radio receiver and a decoder IC. The RLP434A outputs the serial stream into the decoder IC HT6034. The decoder IC reads the serial stream and decides if the source of the message is meant for it based on the ID on the message, which is the first part of the serial trail. Because both my serial encoder and decoder have A0 to A7 grounded, you could say both are set for channel 0. The decoder then decodes the received data and outputs which button was pressed on each of its outputs D8 to D11 active low. The decoder IC also outputs an activity signal each time a button is pressed and stays high as long as the button is still pressed. On my schematic, I show which HT6034 outputs will be connected to the HCS12 inputs. The servos interfacing. This was the easiest part of the project because we had on a previous lab interface a servo motor with the HCS12 and controlled the servo using a potentiometer connected to the integrated analog to digital converter. All I had left to do here was connect both servos to my HCS12, initialize the pole width modulator outputs, and test some values to see them go back and forward. All parts interfacing. Once I had all the individual parts designed, built, and tested, I proceeded to interface them together. In the process, I would ensure that the transmitter signals were visible on the receiver side, and that the receiver signals were also being interpreted by the HCS12. I proceeded to connect the servo motors as on the last slide and did some quick tests on my main code. Once I knew all the devices were correctly interfaced, I proceeded to write code to interpret the signals correctly. The signals from the receiver circuit are active low, so I had to activate the internal pull-up resistors on each of the HCS12 inputs PH3 to PH0. A 0 meant that a button was pressed. I also connected the activity output from the HT6034, which is an active high. Needless to say, I had to activate an internal pull-down resistor on that input pin. Software development. It was best for me to develop this project as what it really is, an embedded system with inputs and outputs. Reducing the system to which inputs and outputs I expected simplified the software development. I also took advantage of the activity output pin from the HT6034. This activity output would edge trigger an interrupt service request that would modify the outputs to the servo motors connected to the pulse width modulators outputs PP5 and PP7 IOs. As you will see on the programming code flowchart, the only way to exit the while loop is for PH7 to be low, and it updates the pulse width modulator output each time it iterates. Because I reduced the code to each possible case of interest, having multiple buttons pressed even after entering the while loop will modify the outputs to the correct case but will not act unexpectedly. Software delays are added for debouncing between read and calls. Once the PH7 is low, the code is exited and the pulse width modulator outputs are dropped to 0% during the cycle, no movement on the servos while no button is pressed. On this slide, you can see a programming flowchart. You can see the input and output initialization. You can see a main loop just doing nothing, and an edge trigger ISR, which basically changes the outputs of the pulse width modulator as the inputs are changed. And it really is a very simple approach, and with the advantage of having the HCS12 be able to do anything else and not have to constantly read the inputs to change its outputs. When no activity is detected on the input pin PH7, the code modifies the output for the pulse width modulator back to 0% and back to the main loop. Frame construction. I found a strong piece of plastic sheet which was cut into a diamond shape. The idea being that it would be easier to get around a corner if it hit anything with the rounded tip. I also used epoxy instead of screws since the plastic sheet is not thick enough for screws. I also used Velcro, double-sided tape, for mounting the HCS12 board. I checked to make sure that there was no continuity on the adhesive part. I also took a tire from an old chair that could spin 360 degrees to balance the car. I also used some silicone grease spray on the tire bearings to decrease the friction. After using the 9-volt batteries once, I switched to a 12-volt deep cycle battery and to 3 LM7805 voltage regulators to keep the entire system stable and within safe voltage and current parameters. The final product. After I waited for some time for the epoxy to dry out, my RC car is now alive. I proceeded to load the code from the Codewater IDE into the HCS12 board on the car and did some tests. I realized I had the tires 180 degrees from each other, so I had to switch the pulse width modulator values reverse for one of the servos. Demonstration video. Here you can see a track diagram and a picture of the track that I use, and if you like to see the videos you can click on the following links. There's the official link and one slightly modified track. Enjoy.